All right, welcome. And now we're going to start Chapter 7, Section C. We're going to talk about the law of large numbers and how that plays in probability. So let's get started here. So what is the law of large numbers? It applies to any process of probability, any probability experiment, anything that involves random chance processes. So it says that the probability of an event, P of A, and the results of repeated trials are independent. So this is based on independent trials that are repeated over and over again. Okay. And what this says is that as the number of trials increases, the relative frequency of the outcome that we're interested in gets closer and closer to the theoretical probability. So in other words, the relative frequency of an event, which is, again, remember that's one of the definitions of probability, that gets closer and closer to the theoretical definition or the theoretical result of the same probability of the same event. So here's an example of when a die, right? So you are rolling a six-sided die, and we know the theoretical probability of rolling a 1 is 1/6. So that's the blue line. You could see the red line, which is the relative frequency, starts off very, what's the word I'm looking for? Sporadic, okay? Goes up and down, very volatile. But as you increase the number of rolls, right, and you're taking the relative frequency, notice that as the number of rolls increases, the relative frequency does start to settle down and gets closer and closer to the blue line. So let's do an example. It says a roulette wheel has 38 numbers, 18 black and 18 red, and with the green numbers, which are 0 and 00. And assume that all possible outcomes are equally likely. Okay, so in this case here, what is the probability of getting a red number on any spin? So since it's independent, right, so each spin is independent, well, we just take the number of red out of the total number of spots that you can get, which there are 38. Right? So out of 38, there are 18 red. So it'd be 18 out of 38, which gives us 0.474. So it's less than a half, right? So 0.474. Now, if patrons at a casino spin the wheel 100,000 times, about how many times will the red number come up, a red number come up? Well, think about it. If the probability is 0.474, one of the other things we could use that probability as is synonymous or analogous to a percentage of the population. So we could say, hey, the probability of getting a red on any one spin of the roulette wheel is 0.474. But another way of saying it is that approximately 47.4% of all spins will result in red. So that means if we have 100,000 spins of the roulette wheel, then we would expect 47.4% of those to result in red, which would be what? 47,400 times. Okay, let's consider two events, each with its own value and probability. Now we're going to start talking about expected value. Expected value is a terminology that's used in all kinds of industries, especially gambling, business, insurance. So the expected value is what we would expect an outcome to be if we did this process over and over again for a long period of time, or over a large number of trials. So the expected value is very simple. It's just you take the event, the value of 1, and you multiply by its corresponding probabilities, right? So you take each event outcome, multiply by its corresponding probabilities, and you take those products and add them up. and that is what gives you expected value. Another term for the expected value, by the way, is the mean of the probability distribution. So let's look at this example of insurance policy. So the cost of the insurance policy has an annual premium of $200. So you have to pay $200 a year to have this policy in force. And based on the data of past claims, the company has calculated the following probabilities. We know they, on an average of 1 in 50 policyholders will file a claim, a $2,000 claim. An average of 1 in 20 policyholders will file a claim of $1,000. And then an average of 1 in 10 policyholders will file a claim of $500. Okay. And so now we're going to create a table of all of the possible outcomes, because remember, we also have the outcome that someone could not make a claim, right? They could go the whole year and not make a claim. So we have to also consider that outcome. Now it says, assuming the policyholder could file any of the above claims, what is the expected value to the company? So this is from the company's point of view. So what we're going to do is there's a couple ways we could do this. Well, let's do the first one here. So it says we let the premium $200 be positive as income because it's coming to the insurance. Remember, we're looking at it from the insurance company's point of view. So this is money coming in. Okay. Now, what are the three possibilities? The three possibilities is what? We could have, let's do X as is the outcome, right? Okay. And so let's say one outcome is no no claim. Oh, let's do the claim. Let's do the other ones first. So we could do $500 claim, $1,000 claim, or $2,000 claim. Okay. So if it's a $500 claim, then what happens? They're going to be out $500. They have to pay $500. Okay. If it's a $1,000 claim, they're going to be out $1,000. And if it's a $2,000 claim, they're going to be out $2,000. And the corresponding probabilities is one is the $500 one is 10 out of 100 because it's 1 out of 10. Okay. The other one is 20 out of 100. So that would be the $1,000 claim would be 20 out of 100. And the $2,000 claim would be 2 out of 100. And the reason why I do it out of 100 is just to make it easy to find the final probability, which is no claim. So the company is out zero money. Okay. And so the probability of that would be what? It'd be the complement of the rest, right? So it'd be 10, 30, 32. So 32 would be 68 out of 100. Okay, and we'll come back to that later. So what they did was they took the expected value of all the claims, right? And then they added the $200 premium, and you get an average or the expected value of $60. So this means what it suggests is policies like this one, if they sold a bunch of policies like this one, on average, they will make $60 per policy each year. Okay, so if you have 1 million policies like this, you'll average over all the 1 million policies about $60 per policy. So you'll average about $60 million a year on profits. Okay. Okay. Now, the other way to do this would be to talk about net gain, right? And I think this is the better way to look at it. So here's the outcome. Here's X, which is, we're going to call that net gain for the insurance company. And then probability of X. So again, we're going to have our 4 possible outcomes, right? So no claim. And then we have $500 claim, $1,000, $2,000. Now, the net gain means that what's the net gain for the company? If there's no claim, the company earned $200. If the company, if they have a $500 claim, the company had to pay out $500, but they did get that $200 back. Right, they did get that $200. So the net gain in that case would be minus $300. And then for the $1,000, the net gain would be minus $800. And then for the $2,000 claim, it'd be minus $1,800. And so if you take, again, the probabilities, it'd be not 48, it'd be 68 over 100. This was 10 over 100. And then the other one was what? 1 out of 20. Oh, I'm sorry, I made a mistake. That should be 5 out of 100, not 20 out of 100. Oh, so I need to adjust that. That's a little wrong. So my math was off on the last one. Hold on. And then this was what? 2 out of 100. So that's 17. So this would be 83. 83. And that should add up to 1. 83, 93. Oh, no. Yeah, 93 plus 7. Yeah, so that equals 100. And so now if you take these, so it'd be what? It'd be 200 times 83 over 100 plus negative 300 times 10 over 100 plus negative 800 times 5 over 100 plus negative, oops, let's do it down here, plus negative 1800 times 2 over 100. Excuse me. And that will give you the same answer of positive $60. Okay, so let's go back here. So this wasn't 68. This was supposed to be 5. 5 out of 100 because it was 1 out of 20. And so that'd be 5 out of 100. And so this would be 83. Okay, but again, it gives you the same answer. All right, now the gambler's fallacy. The gambler's fallacy is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck. This is also known as the law of averages. And the law of averages is a fake law. It's not real, okay? But you see a lot of people that will appeal to this so-called law, and it doesn't work. It's not true. So it says, suppose you're playing a coin toss game in which you win $1 for heads and you lose $1 for tails. After 100 tosses, you are $10 in the hole because you flip perhaps 45 heads and 55 tails. So you keep playing the game. You continue playing until you've tossed the coin 1,000 times, at which point you've gotten 480 heads and 520 tails. Does the result agree with the law of large numbers? Have you gained money back, or have you gained back any of your losses? And the answer is, One, yes, it does. It does conform to the law of large numbers because it did get closer to that 50-50, right? The one half. Okay, but nonetheless, you are further in the hole. Okay, you are further in the hole. So again, just because this is, again, the law of averages is not a real law. Okay, that's the gambler's fallacy. Okay, so even though you got closer to the theoretical probability of 0.48, you were still down more than you started. You were down $10 and now you're down $40. Okay. And again, streaks, right? So here's the thing about independent events. Remember, independent events don't care about how many times you flip the coin or how many times you push the button on the slot machine or pulled the lever on the slot machine or how many times you play the lotto. Your chances of winning don't go up. Your chance of getting heads on the next flip don't change. Your chance of winning the lottery, every time you've played that number, the same number for 30 years, your chance of winning the lottery is the same based on the number of people who buy tickets each week. Okay, obviously that's the only thing that changes the probability, but your chance doesn't change just because you've been playing the same number. If you sit at a slot machine and you keep pushing that button and pushing that button and pushing that button, and you make the same bet over and over again, or whatever the bet is, your chances of winning don't change every time you make that same bet. Okay? So now if you change your bet and stuff like that, that changes things, but still, this idea that as long as you sit on a slot machine or you sit at the roulette wheel and you just keep spinning the wheel and you keep playing the same bet, that somehow your chances of winning or hitting it big go up, it doesn't. It stays the same. That's why I don't gamble unless that's just for fun, which is very rarely. So a farmer knows that at this time of the year in his part of the country, the probability of rain on a given day is 0.5. It hasn't rained in 10 days, and he needs to decide whether to start irrigating. Is he justified in postponing irrigation because his region is due for a rainy day? And the answer is no, because it's based on the gambler's fallacy. It's based on the law of averages, right? Just because he's having a losing streak. However, if we assume that weather events are independent from one day to the next, which often but is not always the case, then the probability of rain is still 0.5 on any given day. Okay, so the region is not due for rain. Okay, keep that in mind. Now the house edge. Now, just like any casino, the casino always has an edge. This is where they tweak the game so that the probability of the house winning is slightly in their favor. Even if it's a little bit, this is a huge deal for the house. It gives the players a sense that they can win, but in the end, because of the law of large numbers and expected value, just like with the insurance policy, the casinos have hired very smart statisticians, analysts, and they know the odds forwards and backwards, and they know that over the long haul, if people keep playing a certain game, they're going to make money. All right, that's it. You have a great day, and I'll see you next time.